Hey everybody, Dr. A here, and in this video we're going to be providing some brief background information on a phenomenon called fatigue, and this is really for the sake of either a mechanics of materials or material science or even a structural engineering setting. So let's go ahead and dive into it. So what is fatigue? Well, fatigue is the behavior characterized by strength degradation of a component due to repeated cyclic loading. Okay, so what does that sentence mean? That first sentence is very important to us. That means that, let's say you have a component of a structure or a machine of some sort, and it's subjected to repeated cyclic loading. Well, over a certain amount of time or over a certain number of cycles, that component can lose strength. Its strength degrades with the number of cycles of load that it's experiencing, and eventually that component can wear out and become damaged or even completely fail. So that whole idea is called fatigue, okay? And we see it pretty commonly in all kinds of engineering designs, okay? So specifically in civil engineering, fatigue can occur in buildings or bridge structures during earthquake loading. Imagine you're in a building and an earthquake occurs. Well, that earthquake causes vibrations in the building, including all or most of the components of the building. And so those components are vibrated, maybe they're accelerated, they've got additional forces cyclically shaking them back and forth, and that repeated cyclic loading can cause material degradation that a static load would not cause, okay? We also see fatigue loading in machine components. Imagine your car or your vehicle. It's got moving gears and shafts and pistons and rotating belts. All of these rotating and moving and translating components of your car cause repeated cyclic loads on the support components, and that can wear them down. That's why we have to take our car to the shop and get things repaired and replaced and fixed. It's due to that repeated loading on those systems, or that cyclic loading on those systems. We also see it in aircraft systems. If you're flying in an airplane and you look out the window and you see the wings of the airplane kind of bouncing a little bit when you take off and land, or when you're hitting turbulence, that's a repeated cyclic loading on the aircraft due to the wind pressure acting on it, okay? So what could that do? That could wear down the components, and then you need someone with that area of expertise to know how to design and repair those kinds of components. So how do we investigate this? Well, a common test to investigate the cyclic loading of something is called the cyclic tension/compression test, okay? And when we perform this cyclic tension compression test, it'll produce what's called a hysteresis plot. So maybe pause the video and say that word. That's a word that we might not have heard before, but hysteresis plot, okay? And I'm going to draw one of those for us here in just a minute. But this plot, this hysteresis plot, shows stress versus strain. So you might be thinking, well, this is like a stress-strain diagram. Well, kind of. It kind of is. But the difference is, instead of a single monotonic tension load like we see in a tension test, you are now cycling through tension and compression loads. So we're cycling through those applied loads with a specified amplitude, okay? And again, I'm going to sketch one of these for us in just a second. Now, we can use this data from this hysteresis plot, or several hysteresis plots, to plot what's called a Wöhler curve. Now, this is named after a German engineer. This is his last name, so I'm sure I'm pronouncing it incorrectly. It's probably something like Wöhler or Wöhler, but I'm just going to say Wöhler curve. And what this curve shows is stress amplitude versus a number of cycles of loading, okay? So let's turn the page here and let's talk about that. Let's say that we have a specimen, okay? And I'm going to draw this one horizontally. Oh, that does not look right. Let's draw this a little bit better. Let's say we have a specimen here, and, it's going to have some cross-section area, A. And let's say that we have this applied load in a tensile and compressive cycle, which means that, we're stretching it and then we're compressing it over and over again for a certain number of cycles, okay? Well, a hysteresis plot of this kind of behavior would look something like this. Let's go ahead and draw a plot over here on the right side. Okay, and we need all four quadrants here, and we're going to put stress on the vertical axis and strain on the horizontal axis, just like we've done before, okay? And so what happens is, if we first put this tensile load up to a certain magnitude or amplitude, then we're going to have this linear elastic region that develops just like we have studied before. Well, let's say that this is the amplitude right here. This is, sigma A for amplitude. And then what we do is we cycle back and we cycle it down to the compressive sense, okay? And again, this is sigma amplitude here, okay? Now, let's say that we keep cycling this over and over again. We keep going back and forth, back and forth. Well, eventually, this specimen will fail somewhere, okay? And also eventually, this plot will not be perfectly linear at some point. It's going to start having a little bit of spread and a little bit of nonlinearity like you see me sketch here, okay? So that would be at a constant amplitude, sigma A, all right? Now, if I were to plot this, as a sinusoid, what would that look like? Well, that would just be like the plot of a sine graph, right? So if I were to maybe sketch that out as well, hopefully we remember our basic trigonometry, okay? So, this would look, something like this. And then it would just continue on, okay? Now, where is that sigma amplitude here? This is the positive and this is the negative, right? And remember, this is the amplitude right here. It's the height of the crest for each one of those segments of the curve, okay? So, and then, of course, this axis here would be time right here. And we just keep on and on until we either cut the experiment off or the specimen itself fractures, all right? Now, what we can do is test several different specimens, and we can test them at different amplitudes. So how about I call this, amplitude 1. So I'll put a little subscript 1 under sigma A1 there, okay? So let's say we take another specimen that's made of the same material, all right? And let's go ahead and draw that here. And we're going to, cycle through tension and compression again, right? Tension, compression. And let's say we generate another hysteresis plot. Let me sketch this a little bit better for us. We're going to sketch another hysteresis plot. But this one is going to have a different amplitude, okay? So there's epsilon. Now, let's say that we make this amplitude larger, all right? So if we make this larger, we'll have this linear portion, and then maybe it goes a little nonlinear, all right? And then we unload it, and it comes down here into the compression zone, goes nonlinear. We reload it, and we keep doing this, okay? Over and over again, and we keep generating this loop until, boom, it fails somewhere, okay? And let's say it, fails at some point in those cycles, all right? So this amplitude, this is still sigma A, except it's sigma A2. This is sigma A2, in the negative direction, okay? And then, of course, we could have a similar sinusoid that shows the behavior with time, all right? So if we were to sketch this out and show this sinusoidal relationship, here's sigma, here's time, and, let's say we have a larger amplitude here, okay? Larger amplitude, dot, dot, dot. Okay, these are supposed to be smooth curves, by the way. So sigma A2, sigma A2. So let's say we perform several of these tests, okay, and we generate several different hysteresis plots, okay? Well, then what we can do is generate this Wöhler curve or Wöhler curve, however we're going to pronounce it correctly. Hopefully one of those versions is the correct pronunciation. But we're going to generate this curve that shows that stress amplitude, right? This is sigma sub A versus the number of cycles it took to fail that specimen, all right? And so if we were to plot that, what is that going to look like? Well, if I were to sketch that out, then, maybe we'll have this axis here, and we're going to put this other axis here. So this is going to be the stress amplitude here. So this is that sigma sub A. And then this horizontal axis is going to be the number of cycles, okay? The number of cycles of each specimen until failure, okay? And so what's going to happen is you're going to get these, data points that form this curve of some sort, okay? And this is going to be, a pretty nonlinear curve that smooths out like this, okay? And so what does that tell us? That tells us that at higher stresses, we're going to have fewer cycles to failure. And then at lower stresses, it takes more cycles to fail the specimen. So let's write that down, okay? So at higher stress amplitudes, that's sigma sub A, it takes fewer cycles in to fail, okay? And then, the opposite is true to it at lower stress amplitude. So you're down here at a lower stress, it takes more cycles to fail, okay? So basically what you end up reaching is a fatigue limit, okay? A fatigue limit. So let's write this down. The fatigue limit, where does that occur? So it occurs at lower stresses and high cycles and defines the limit when fatigue failure will be unlikely. So where is that going to be? That's going to be, like right here, okay? This will be like the fatigue limit. Let's write this down. Fatigue limit, okay? Now, what you can also determine is the fatigue strength, okay? The fatigue strength. So let's write this down. The fatigue strength is the stress value. So that's, a sigma amplitude value at which failure occurs at a specified number of cycles. So for example, if you want the fatigue strength at a particular N value, N sub I, you can go to this plot with N sub I, move over until you hit the curve, and then get this fatigue strength value right here, okay? Fatigue strength. All right. This is the concept of fatigue loading. Now, again, this is not everything by any means. This is just meant to give you a brief introduction to this concept for the sake of mechanics of materials or material science or even structural or aerospace engineering at the undergraduate level. If you go into graduate school in any of these fields, you'll likely end up taking a full 3 credit hour course at the graduate level in master's or PhD on just fatigue analysis. Now, another name for this that you might come across, sometimes these are called SN curves, okay? So we're going to put a note here. We're going to say this is also known as a fatigue life SN curve, okay? S is for stress, which is just sigma here, and N is the number of cycles. Another thing to note is that the number of cycles is usually shown on a log scale, okay? So we'll put a note here, typically on a log scale. All right, so that concludes this introduction to fatigue analysis. Hopefully you found this helpful. If you did, please hit like and subscribe and be on the lookout for other content like this. Thanks for watching.